Hello everyone, welcome to this video. In this video, we'll be proving property 5th under a homomorphism, right? So here they are saying phi of A would be equal to phi of B if and only if we have A kernel phi is equals to B kernel phi. Now notice that if this is a subgroup and A is some member from the group G and B is also some member from the group G, then A kernel phi is a coset and B kernel phi is also a coset, right? So we have to prove the if and only if case. So let's start by assuming that phi of A is equals to phi of B, and we will be proving that A kernel phi is equals to B kernel phi. So here, because phi of A we have assumed to be equal to phi of B, so what we can do, we can pre-multiply both sides with phi of B whole inverse. So you see this and this both they result in identity. So you have whole of this thing as equal to identity, right? This is what I have written over here. So what does it mean? It mean that you can take this power inside, right? You can do that, and then you can club up the elements, so it would be B inverse A. So from here you obtain phi of B inverse A, phi of B inverse A is equals to E. So what does it mean? It means that this B inverse A would belong to kernel of phi, right? And using this result here, if you have A inverse B belonging to some subgroup H, then AH would be equal to BH. These two cosets would be equal to each other. Hence from here you can clearly say A kernel phi is equals to B kernel phi, and you can reverse the steps here in order to prove the opposite result. Why? Because you can suppose that A kernel phi is equals to B kernel phi. So using this result, again you have B inverse A belongs to kernel phi. If B inverse A belongs to kernel phi, so what does it mean? It means that phi of B inverse A is equal to identity. So you can write phi of B inverse A as phi of B inverse into phi of A, that is equal to identity. So you can write it like this: phi of B whole inverse into phi of A is equal to identity, correct? So you can pre-multiply both sides with phi of B to obtain phi of A is equals to phi of B, and this is what you wanted to prove in the converse part, right? Moving forward on to our sixth property, the last property for this theorem, we have if phi of G is equal to G dash, this is given to us, then we have to prove that phi inverse G dash is equal to G kernel phi. Now what is this set? It consists of all the members X from the group capital G such that phi of X is equals to G dash, correct? Okay, so now in order to prove that phi inverse G dash is equals to G kernel phi, right, we will prove the two inclusions. First of all, that phi inverse G dash is contained in G kernel phi, and G kernel phi is contained in phi inverse G dash, correct? So let's move on to our first inclusion. We assume that some element is present here. Let's call that element as X, and we will prove that this X is also present here. So it will prove this inclusion. So here we assume that X is present in phi inverse G dash. So what does it mean? It means that phi of X is equal to G dash, right? So by the definition here, if you have X belonging to this set, so definitely phi of X would be equal to G dash. So from here, what is the definition of G dash? You see, we have assumed G dash to be equal to phi of G. So you can write it phi of G here. Now using the above property, if two phi are equal to each other, then their corresponding cosets are also equal to each other. So if phi of X is equals to phi of G, then phi X kernel phi would be equal to G kernel phi, and from here you can clearly say X belongs to G kernel of phi using the properties of cosets, correct? So we started by taking some arbitrary element X in phi inverse G dash, and we end up at getting it present in G kernel phi. Hence phi inverse G dash is contained in G kernel phi, as X chosen was arbitrary member. Now to prove the opposite, we wanted to prove that G kernel phi is contained in phi inverse G dash. Again what we do, we take some element here and we prove that it is present over here. And let's first of all take some element here in kernel phi. So let's take this small capital K present in kernel phi. So then phi of gk would be what? Phi of gk would be phi of g, phi of k, right? And what is phi of g? By the assumption phi of g is equal to g dash. So phi of g is g dash, and what is phi of k? Phi of k, k is present in kernel phi. So phi of k is equals to e, correct? So we have e here, and g dash e is equals to g dash. So from here you get phi of gk is equal to g dash. Hence you can say gk is equal to phi inverse of g dash, correct? So according to the definition given here, if you have phi of gk is equal to g dash, so that means this gk would be present in phi inverse of g dash according to the result, correct? So gk is present in phi inverse of g dash. So what does it mean? Because k was taken from kernel phi and it was an arbitrary member, hence g kernel phi is present in phi inverse g dash for all the member small k. Hence we have this inclusion. Therefore both the inclusions now give us the equality which we wanted to prove here in this particular case. So I hope you understood all of these properties well. Well, that is it for this video. Thank you for watching.